In the last experiment, we found that the equation of motion for the puck moving along a one-dimensional path, with no influence except for initial motion state, is given by the equation x of t is equal to v0 times t plus x0. We can calculate the velocity of the particle using the equation v of t is equal to the first derivative of x, or dx of t dt, which is equal to the derivative with respect to t of v0 times t plus x0, which is the constant v0. Therefore we conclude that the velocity of the puck in the last experiment was constant. Now let's use the scientific method of performing more experiments, and seeing if our results are repeatable. We will start from different initial positions, pushing the puck harder and softer, or in other words changing its initial velocity v0. In the first experiment, the initial position is 0.91. And the initial velocity is 0. The plot of position versus time is shown as the white horizontal line. In our second experiment, the initial position is 0.68. And the initial velocity is 0.2. The plot of position versus time is shown as the cyan line. We can do 3 more experiments, getting a yellow, purple, and green line. We observe that the plots of position versus time for all the experiments are straight lines, with the equation of x versus time given by the straight line equation x of t is equal to v0 times t plus x0. x0 and v0 are different for each experiment. Note that if we push the puck very hard, as we did in the last experiment, the equation of motion is still x of t is equal to v0 times t plus x0. And if we don't push the puck at all, as we did in the first experiment, then the equation of motion is still x of t is equal to v0 times t plus x0. But v0 in this case is 0, implying that the position of the puck is constant in time. Therefore, we can conclude that the velocity of a particle moving on a straight line one-dimensional path, with no other influence except for an initial motion state, is constant. This also implies that all higher-order motion derivatives, v dot of t, or acceleration, v double dot of t, etc. are 0. The one-dimensional path that we chose in the previous experiment was a straight line. So what if we use a circular one-dimensional path? Or even an arbitrary curve? In both cases, we will keep the rest of the experimental conditions the same, namely, no normal reaction forces, no friction, no air resistance. The path is horizontal, so there's no gravity, no electricity, and no magnetism. The only influence is that of an initial motion state. Will we reach the same conclusion of the last experiment? Let's find out. First, let us use a circular path. Let's push the puck, starting from different positions around the circle, and with different initial velocities, and then plot the puck position along the path versus time. As you can see, for each experiment, the plot of position versus time is a straight line. Now let's repeat the experiments, using the curved path shown here. Again, we'll push the puck, starting from different positions along the path, using different initial velocities, and plot the puck position along the path versus time. As you can see, the plot of position versus time is still a straight line. The equation of this straight line is given by x of t is equal to v0 times t plus x0, implying that the velocity v of t is constant. Therefore we conclude that for a particle moving along a curved one-dimensional path, with no influence except for initial motion state, the velocity is constant. Now let's do the same experiment. But let's vary the mass of the puck. We observe that the results don't change. The equation of motion is still given by the equation x of t is equal to v0 times t plus x0, which implies that the velocity of the puck is constant. And so we conclude that for a particle of arbitrary mass, moving along a curved 1D path, with no influence except for initial motion state, the velocity is constant. Here is our general conclusion from the particle on a one-dimensional path experiments that we described. A particle moving along an arbitrary one-dimensional path, with no other influence but an initial motion state, will move at a constant velocity along the path. In other words, v of t is equal to v0. This implies that the particle obeys all constant velocity relations derived earlier. Click on the shown link to review that section. Note that the path can be any general one-dimensional curve. Let us again recall our assumptions. The particle encounters no normal reaction forces along the path. In other words, there are no obstructions in the path. Friction between the particle and the path is negligible. Air resistance is negligible. The path is horizontal, such that gravity effects are not present. No electric effects are present. And finally, no magnetic effects are present. The previous set of experiments illustrated the scientific method of performing experiments and deriving general theories from these experiments. In the scientific method, we first observe a certain phenomena, like a puck moving along a one-dimensional path, under certain controlled conditions. Where the controlled conditions in this case are that the puck is restricted to moving on a 1D path that can be either curved or straight, with no other influence except for an initial motion state, and that the initial position and velocity of the puck are arbitrary. Then we reach some conclusion, which in this case is that the plot of position versus time, for any arbitrary initial position and velocity of the puck, is a straight line, which implies that the velocity is constant. Then we performed more experiments to ensure that this phenomena was repeatable. We found that it was indeed repeatable, and concluded that x of t is still v0 times t plus x0, and v0 is constant. And from that we made a more general observation, that for a particle moving along a one-dimensional path, with no influence except for initial motion state, the velocity is constant. Here are some examples of how our experimental observation is relevant to everyday life objects. A bowling ball, after it is tossed, moves at a nearly constant speed from the time it leaves the bowler's hand to the time it hits the pins. A curling stone, when given a push, moves on ice for a long distance, at nearly constant velocity. A skater continues to move across any icy surface at nearly constant velocity, even though nothing is pushing him or her. Now you can try doing the experiment yourself. Let me explain how to use the virtual experimental setup. First, make sure that you are close enough to the experiment, in order to manipulate the controls. Then enable the experiment by checking the box labeled Enable 1D Track. On the right-hand side is a graph of the puck's position versus time along the track. You can set the maximum time on the graph using the shown slider. To increment the value, left-click on the slider. To decrement the value, hold the Shift key down, while left-clicking on the slider. Alternatively, you can use your mouse wheel to increment or decrement the value smoothly. To do that, hold the left mouse button down while rolling the mouse wheel away from you, to increment the value, or towards you to decrement the value. You can also quickly set the value to its ending or beginning range, by holding the left mouse button down while pressing either the right arrow key or the left arrow key, respectively. In a similar way, you can set the initial position of the puck, the initial velocity of the puck, and the angle of the rail, where an angle of 90 degrees means that the track is vertical, and an angle of 0 means that the track is horizontal. Lastly, you can set the coefficient of friction. When you are ready to run the experiment, press the restart button. When you are ready to continue with the lecture, press the play button on the top navigation bar.